Welcome, gang, to the next lecture of artificial intelligence. Today we're going to be talking about perceptrons, and we're going to be getting much more into the heart of the matter computationally, I guess you might say. So let's see if I can get my slides up. By the way, you know, we always stand the chance of Mike's internet going out, so I would strongly encourage you, like I always do, to download the notes so that you have them in front of you, so that if my video goes out and I lose the ability to show you things, you'll still have all of what I'm talking from, including all of the images available to you. So please do that. Okay, let's see. I need to share screen, and here we go. If I can find the button to go. Okay. All right. So we began, or we ended, I guess, last time with this little model of a neuron. This is a brain cell, a neuron, and a neuron. Can you guys see my my cursor or not?
Yes.
Yes or no? You can see the cursor. Oh, good. All right. So these little dendrites here are where other neurons would be connected to this neuron. So these are kind of the input ports of the neuron, and the neuron, when it gets enough inputs of the right type, it will fire. It will send an electrochemical impulse down its axon, and that'll go to these little things here, and they sit up next to the bodies of other neurons. And the gap, I don't have any other neurons drawn here, but if I had another neuron, say right here, drawn, the gap between this little thing and the dendrites from the next neuron would be called the synaptic gap. And basically what happens is these things have little vesicles, little capsules of neurotransmitter that they can release, and the neurons whose dendrites are next to this guy will pick it up, and they then can take that input and do whatever they do with that input. Okay, now how do we model it? Well, we model the neuron by having a number of inputs. You can have n, any number of inputs, so I have 1 to n here, n inputs. And these inputs can be numbers. They can be negative, they can be positive, they can be 0, they can contain fractions. So this could be 27.342, for example. It doesn't have to be an integer. It can be 0. It can be a negative number. So basically, any real valued number can be an input value. Every input has a weight associated with it. So x1 has weight 1, x2 has weight 2, x3 has weight 3, all the way down to the last one, xn has weight n. And what the neuron does is, well, the biological neuron is set up so that some synapses are inhibitory, some synapses are excitatory, but eventually, if the inputs pass some threshold, okay, then the neuron fires. Well, we simulate that by saying we will take the weighted sum of each of the inputs. So x1 times w1, x2 times w2, x3 times w3, xn times wn, and we add all those up. So they go into a summation unit here. So this summation unit simply has the weighted sums of the input, the weighted sums of the inputs. And then those inputs, the sum of those inputs, that number, it will be a scalar, that number will be compared to a threshold. This is a threshold comparator. That's the symbol for a threshold comparator from electrical engineering. And so if the sum of the inputs is greater than the threshold or equal to it in our model, then the neuron fires. So basically what the neuron does is it takes a weighted sum of the inputs, compares it to a value, to a threshold, and if that weighted sum of the inputs is greater than the threshold, or equal to in our case, then the perceptron fires. And that's all a perceptron does, is it's a very simple thing, takes a weighted sum of its inputs, compares them to a threshold, and if the weighted sum is greater than the threshold, or in our case equal to, it fires. That is all a perceptron does. Is there any questions? Are there any questions about that in and of itself as to how the, I guess I have to stop sharing momentarily. Are there any questions about that? Okay, I don't see any questions. Going one more time. I can't really see the chat when I'm sharing my screen, so that's why I'm popping back here. Okay. Back to screen share mode. So again, that's what a perceptron does. And here I just have them, a mathematical representation of the same in-input perceptron. Here on this slide, I have it shown graphically. Here, I just have it mathematically. So mathematically, it's a function, f of x, right? Where again, x would be a vector in this case, right? An n-dimensional vector. So it's a function of the vector x, and basically it computes that function. The output of that function will either be a 1 or a 0. So even though the input to perceptrons can be real valued numbers, the output of perceptron is either a yes, I fired, or no, I didn't. Okay, so that's an important thing about a perceptron. And in what case will it have a 1 as an output? Well, where the sum, as I goes from 1 to n of x sub I times w sub I, the input times the weight, if the sum of all of those is greater than or equal to, that's not a 0, that's a theta or threshold, then the thing fires. So this is kind of, showing it. You can see in your mind how you would program this, right? You have a little for loop. You go from 1 to n, and each time through the loop, it would add to a sum. The current input, x sub I, times the current weight for that, w sub I. It would multiply those together, add them to the evolving sum. After you finish the little summing loop here, you would compare it to theta, and if the sum was greater than theta, or equal to, in our case, greater than or equal to, then you would return a 1. Otherwise, you would return a 0. Again, x is the input. It's expressed as a real number, positive, 0, negative. W sub I, well, actually all of the w's are a weight, expressed as a real number, positive, 0, or negative. Theta is a threshold, and it's expressed as a real number, 0, positive, or negative. So if you want to understand what a perceptron is, again, all it is a weighted sum of the inputs, which are compared to threshold theta, and if the weighted sum of the inputs is greater than or equal to theta, it fires. All it does, very simple. You can imagine implementing it as a little loop. As we'll see in a little while, as we'll see momentarily, another way of viewing it is as a dot product of two vectors, the input vector x and the weight vector w. So you can show it as a vector multiplication if you want to do it that way too. I'll talk about that in a minute. Okay. So sorry, my voice is a little funny today. You know, I think the deal is that since I'm essentially in quarantine, right, and spend all my time here at home, I don't talk very much. I mean, I don't. And so when I get ready to lecture, my voice isn't really used to talking a lot. So that's why I sound so funny. And I'm coughing all the time when I try to talk. It's like, oh yeah, talk. That's what humans do with one another. Okay. So what are the effect of the input of the weights on the input values? Well, remember going back to the basic model, I said that some of these synaptic gaps between neurons will be excitatory and some will be inhibitory. What do I mean by that? Well, excitatory means that if a neuron that would be over here fires, right? So the inputs come into these dendrites here. Well, the fact that the neighbor neuron fired will cause this neuron to be more likely to fire because this would be an excitatory synaptic gap. The guy next to you, or maybe the girl next to you, the neuron next to you firing next to this gap would make you more likely to fire. It's excitatory. But there could be some other neuron over here, and maybe the synaptic gap for it is not excitatory. It's inhibitory. So if the guy over here, if the neuron over here fires, that might make this neuron less likely to fire. Okay? And that's why our weights can be either positive or negative. If a weight is positive, right, an input, a non-negative positive input coming in here would add to the sum and make it more likely to exceed the threshold and more likely to fire. But if the input here is positive and this weight is negative, right, that multiplication would give you a negative number, which would essentially subtract from the sum so far, right, making it less likely that you would reach the threshold and fire. So we have excitatory and inhibitory capabilities in our modeled neuron as well. And if you look at it, if you just think about having positive inputs, okay, then if you just think about positive inputs, then a positive weight models an excitatory synapse, and a negative weight models an inhibitory synapse. Large positive weights will increase the effect of a positive input, while smaller positive weights decrease the effect of a positive input. So let's say this guy has a 5, right? And let's say its weight is 2. So 5 times 2 is 10 we're adding here to the sum so far, right? But let's say this was still 5, but let's say that this was 1. The weight is only half as big as it was. It was 2 and now it's 1. Well, then that's only going to add 5 here, right? And let's say maybe that the weight here is 0.2. Well, in that case, your input of 5 is only going to give you a 1 here, right? So when you're dealing with positive inputs, larger positive weights will represent a more excitatory synapse. It will amplify this input, right? Making this neuron more likely for the sum to exceed the threshold and the neuron to fire. Smaller positive weights giving positive inputs make it less likely that it'll fire. And if you go negative, right, that even increases, well, it decreases the likelihood that the thing will fire. So again, let's say we have a 5 here, but instead of being, 2 or 1, let's say that it's a -1. Well, now that 5 is actually subtracting 5 from your sum so far. So a negative weight, when you have positive inputs, is really modeling the inhibitory synapses. Now let me ask the question, what if the weight is 0? What's the effect of of input x1 if weight 1 is 0. What will the effect of that be? Let's see what we said here. Well, the effect is 0. That's right. So in other words, what will happen in that case is it's not an important input. That's exactly what you're saying there. You're saying, I am going to ignore this input. That's exactly what you're saying in that case. If the weight is 0, that particular input is totally ignored. That is the effect. You might say, why would I want to ignore an input? Well, maybe for this particular problem, that particular input isn't in any way relevant. Okay. So, come on. So a weight of 0 causes the perceptron to ignore an input, what we just said. Negative weights decrease the likelihood of the perceptron firing. Again, while we're talking about positive input values. Now, if you want to consider negative input values, these roles flip. With positive weights becoming inhibitory and negative weights becoming excitatory. That's just a feature of the way the model works. It's normally and the inputs can be negative. So you have to be aware that sort of the role of a positive or negative weight plays flips depending on whether or not your input is positive or negative. So you do need to be aware of that. So at this point, you might say we now know everything we need to know about a perceptron. We know how it functions. It's extremely simple. You now know everything you need to know about how a perceptron functions. Okay, well, that took about 15 minutes, 10 minutes of our lecture. So are we done yet? No, we're just getting started. And why are we just getting started? Well, we talked about the history of perceptrons last lecture, so now we're about in the 1930s, early 1940s, where McCullough-Pitts neurons had been described, but no one knew how to set the weights on them except by hand, manually. And so that's where we are right here. So all of the fun is going to be talking about, well, how do you teach these damn things to do anything? Right? And that is what Rosenblatt came up with in the late 1950s, the perceptron learning rule. Now, before we get to the learning rule, there's one thing that we want to change, okay? If you look at the model that we began with, right, and if you ask yourself, what does this perceptron actually know? What does it know? Or if you're thinking about it as writing a program, what variables would you need? Well, you would need a variable for each weight, or you could think of it as a vector, a single weight vector, right? So you need that, and you need the threshold value, that little theta that we talked about. So that's fine, and you can easily do that. But rather than have two separate kinds of data, a vector of weights and a scalar threshold, some bright person said, can't we just make everything be in one format, everything that the perceptron knows? And so what we do is we can get rid of the threshold if we convert it into a weight and have a special input, x sub 0, always set to 1. What do I mean here? Well, if we look at this thing here, we can have an x sub 0 set to 1. So we still have our input vector like before. We still have our weight vector like before. I haven't changed anything there. But I'm saying I'm going to have one more input, x sub 0, and it's always going to be 1. You can never change that input value. It'll be 1. And then if you do that, then the weight that you need to have here is equal to minus your theta value. Minus your theta value, wait, what are you saying, Mike? Well, in the original model, let's say that our threshold was 10, okay? So the weighted sum of the inputs had to be greater than or equal to 10 for this thing to fire. In our revised model, we're going to use minus 10 as the weight here, and x sub 0 will always be 1. And what we will be saying here is that, okay, the weighted sum of the inputs, including weight 0 and input 0, which is always 1, the sum of that has to be greater than or equal to 0. This little image is a little bit different than this image, because this image indicated that your threshold is a variable threshold, that you can change the threshold. This indicates that you have a fixed threshold, and the threshold is always fixed at 0. So instead of needing to be bigger than 10, if I subtract 10 from the weighted sum, right, then as long as I'm greater than 0, I'll have exactly the same result. So mathematically, this is saying, okay, it's exactly the same as before. We have a function of a vector x that will return a 1 or a 0. It returns a 1 if the sum. Now notice I'm starting at 0, where before I was starting at 1, right? So I goes from 0 to n, x sub I times w sub I, where the original w sub 0 will be set to minus theta. If all of this is greater than or equal to 0, I fire. Otherwise, it'll be negative and I won't fire. And I haven't really changed anything except to introduce this new x sub 0, which is always set to 1, and w sub 0, the weight sub 0, which is initialized to minus the threshold, minus theta. That simplified our model a little bit, because now everything that the perceptron needs to know is in the weight vector, because the first position of that weight vector is minus threshold, and the first input will always be 1. So basically, what you will be doing is you will be computing the sum, right, the weighted sum, and then subtracting the threshold, and then comparing to 0. But mathematically, it's exactly the same. Now, why would we want to do this? Because we have now reduced the question of whether a perceptron fires to simply looking at the sign of the dot product of vectors x and w. If the sign is positive, the perceptron fires. If the sign is negative, it does not. This is the whole thing, right, expressed mathematically for what a perceptron does. It is a dot product between the input vector and the weight vector. And all we have to do is look at the sign of this dot product, and it tells us whether the perceptron fires or doesn't fire. Okay. Let me see. Are there any questions?
Yes, Dr. O'Neill, I'm a little bit confused. So the threshold is no longer adjustable in this case. It's set at 0. And so what is the, that when I is equal to 0, that weight, and it's equal to negative threshold 0, what is that? How does it exactly work?
No, let's be clear. You are almost right, but I think I see where your confusion is coming in. Okay, you've almost got it, but I think there's a little bit of confusion. The threshold here is 0. So the weighted sum of the inputs will be compared to 0. So it's fixed at 0. But you haven't really removed the threshold from the perceptron. You've just moved it to be a weight. So it's a weight, just like all the other weights. but what should that weight value be? Well, whatever you wanted your threshold to be, make it a negative, subtract it. So think about this. If I need to have something, you know, if I have a sum that adds up to 10, right? So 10's the threshold that I'm going to compare against, right? Then if I have a sum that adds up to 10, let's say my threshold is 5. Since 10 is greater than 5, it'll fire. But now let's say that we do it the way that I'm showing here. So instead of the threshold being 5, I will compute my 10, subtract my 5, giving me 5. Well, that 5 is still greater than 0, so I fire. So it's not changing anything. It's moving what was a variable threshold into a weight. It's moving it into the first position of the weights of 0. So your threshold has now just become another weight, and that allows you to do this really pretty mathematical thing here, where your input vector times your weight vector, look at the sign of it. Notice there's a 1 here. That doesn't say x sub 0, that says 1, because the x sub 0 will always be 1. And this w sub 0, it would be minus theta, minus your threshold. So subtracting your threshold and comparing to 0 is the same thing as computing your weighted sum and comparing it to the threshold. You haven't changed anything. It does the same thing. It's just a little cleaner and simpler. I think I'll give an example here. So you can see that the fixed and variable threshold perceptrons are exactly equivalent. Why? So let's say we've got a variable threshold that's set to, well, just like I pulled out of the air, 5. So my theta is 5. And its computation would be defined by this guy here, where notice I don't have an x sub 0. I'm doing x sub 1 times weight sub 1, x sub 2 times weight sub 2, x sub 3 times weight sub 3, dot, 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 x sub n times weight sub n. Add all those puppies up. That's my sum of my inputs, the weighted sum of my inputs. Compare it to 5. That's my theta value. If it's greater than or equal to 5, fire. Okay? Well, we can say exactly the same thing mathematically, where we take this 5, we make it weight sub 0 as negative 5. The first input, x sub 0, will always be 1. And so now I'm doing the same computation I was doing here. So this part, everything except the first term, is going to add up to be whatever. But then I'm subtracting 5 from whatever this is. So instead of comparing it to 5 like I was going to do originally, since I'm subtracting 5, I can just compare to 0.
That makes sense.
Okay. Does anybody else have a question about that? It's just a little mathematical trick to make, just a little architectural trick to make the mathematics work out better. And so now you can say everything the perceptron knows is this weight vector. That's all it knows, is this weight vector. That's the only thing that changes from perceptron to perceptron, is what this weight vector is, because the first weight slot now is the negative threshold. And we never let this first thing vary here. It's 1. Okay. Thus, in general, a perceptron will fire when blah, 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 everything is greater than or equal to 0, where W sub 0 is minus the threshold, or negative theta. Okay. So now we know everything we need to know about perceptrons, and we can start talking about the perceptron learning rule. So pretty much everything else in this lecture is us working our way through the perceptron learning rule. And this, again, is what Rosenblatt developed in the late 1950s. So the first thing we need to say is, what is a perceptron? A perceptron is a single layer feed-forward network where inputs flow from left to right. Let's make sure that makes sense. It's a feed-forward network where inputs flow from left to right. That's exactly the way we've modeled it here, okay? the perceptron learning rule can train a perceptron by adjusting the weights in a single layer. The perceptron learning rule is going to adjust all of these weights in order to help the perceptron, not help, in order to make the perceptron learn. Okay, now, how are you going to learn? Well, you're going to learn just like you teach a little kid, okay? When your son or daughter or niece or whatever does something that you like, you encourage that behavior. And when they do something that you don't like, you discourage that behavior, right? These days, you have them stand in the corner. When I was a child, you had them spanked. But anyway, you are inflicting pain, either emotional pain of separation or physical pain, right? In a spanking. But you're giving feedback that says avoid this in the future, right? When something naughty happens. But if something good happens, you get a piece of candy or something like this. Or I'm saying child. Let me change it to say when you're training a pet. Maybe that's a little less controversial, right? Although I don't know how you put a cat in timeout. That's water spray to the face, maybe. I don't know if that's considered cruel these days. Okay, so essentially, when you train a perceptron, you do it over training data, okay? And that training data is called a training set. Sometimes, usually, most of the time, if you have a large amount of data, you will also reserve some of it as a testing set. We're going to get into this a lot deeper later on when we start getting into multi-layer neural networks and stuff like this. But the basic idea exists back here in perceptrons. The original data that you have is data that has been correctly classified by a human or some other process. So you've got a lot of inputs that have been correctly classified. If we go back to that old black and white video that I showed you that showed an early perceptron, remember the pictures of men and women. And so when they give it a picture of a guy, and then the human would say, this is the correct answer, male, right? And so that's an example of a training example. And normally it's an automated system where you've got an input, you've got a label, and you automatically compare the input and the label, right? So you can imagine a digitized image with a label male or female, and so you don't have to have some human flipping a switch and telling it. You can just run through thousands of examples automatically because each example has a label on it. So if you have a lot of data, frequently what you'll do is you'll train the perceptron, and then you'll reserve some of your data as a testing data. So data the system has never seen before. And after you're getting good results on your training data, after you've trained it and you think it knows what you want it to know, then you give it examples it hasn't seen before and you see how well it does. So that's generally what you do. You train over lots and lots of training examples that have been pre-classified so that the learning algorithm can know if the perceptron got the right answer or the wrong answer, and then it uses that to teach the perceptron. Essentially, all it's doing is changing the weight vector. But eventually, you hope that it can classify all of your training examples properly. And once it can do that, then you start showing it testing examples that it hasn't seen before, and you see how accurate it is on that. So maybe you've trained it on the training set and it gets 100% of the training data correct, but you give it examples it hasn't seen before, and maybe it's only 97% accurate or 98% accurate. That can happen. So the training set is a set of correctly pre-classified inputs that we use to teach the perceptron to distinguish between the two types of inputs. Now notice I'm saying here between two types of inputs. Perceptrons have only a single output that is either a 1 or a 0. So that's the two classes, either a yes or a no, either a male or a female. Now you might say, Mike, couldn't I train a bunch of these perceptrons? And you could, but the perceptrons themselves don't interact with one another. We'll talk about that. So the model that I'm using is showing training happening on a single neuron, on a single perceptron, but the perceptron learning rule really only applies to single perceptrons. It doesn't apply to multi-layer networks of perceptrons, or even if you could somehow think of a single layer of perceptrons, each one is actually trained independently. The perceptrons in that single layer don't communicate with each other in any way. There's no feedback mechanism between perceptrons in a single layer perceptron network. So the algorithm works on single neurons. And because of that, you can begin to see why, as we'll get to, as we've talked about over the history of these things, there are strong limits to what you can do, because essentially you have like one little neuron. You can have lots of inputs, you can have lots of weights, but it's essentially one little neuron. Okay, let's see. So the training set, the testing set, obviously, I'll say it, but this should be obvious to you. The testing set and the training set should be disjoint. In set theory, disjoint, they don't overlap. So your training examples should be completely separate from your testing examples. You shouldn't mix these two sets up, or you're not going to really, or you're going to be defeating the purpose of having testing data that you've set aside to begin with. Okay. So how does the perceptron learning rule, how do you apply it? Okay. We still haven't described what it is, but assuming we've got it, how do you use it? Well, a high-level way of looking at what a perceptron does is it's a four-step process. At the beginning of the training process, the perceptron makes random guesses as to whether or not it should fire when presented in with a particular input. Operationalize that, Mike, for me. What do you mean by that? What I mean is when you begin training, all of the weights, including the threshold weight, are set randomly. You don't know what they're supposed to be, right? So you just set them randomly. You might say, well, what if I set them all to 1, or even worse, what if I set them all to 0, which means ignore your input? Isn't that going to blow things up? Well, one of the nice features of the perceptron learning rule is that it doesn't matter, ultimately, what you set your weights to. If the problem is learnable, if it's a perceptron learnable problem, the perceptron learning algorithm will converge to the solution. That's a fancy way of saying if it is possible for a perceptron to solve this problem, the perceptron learning algorithm will solve the problem regardless of what initial weights you start with. Now, you might get to a solution faster if your weights are closer to what they need to end up being. You don't know what they need to end up being. You've assigned them randomly. If they're further away from what they need to be, then it may be that it takes longer for the perceptron learning rule to adjust the weights so that the perceptron can correctly classify its inputs. But so it's a matter of how quickly you reach how quickly you train the perceptron. That will depend on what the weights are. But whether or not it's trainable has nothing to do with the initial weights that you set this at. And we'll go through the math of it and eventually, and you'll see that what I'm telling you here is totally honest. Okay? So it's just sort of a matter of efficiency. Since you don't have any idea what the weights should be, you set them to random values. normally. So that's step one. At the beginning of the training process, the perceptron weights have been set randomly. So essentially, it just makes random guesses as you give it examples from the training data, right, as to whether or not, as to what to do on a particular input. So as you would imagine, when you get started, it's going to make lots and lots of errors because it doesn't know anything. It hasn't been taught. Step two, all of the inputs in the training set are presented to the perceptron and any mistakes made are noted. It's one way of thinking about it. You're going to note the mistakes that the perceptron makes. After you've completely gone through the training set, if the perceptron misclassified any inputs, its weights, including the threshold weight W0, will be adjusted by this perceptron learning rule that I keep referring to but haven't shown you yet. After being adjusted, the training set will be presented to the perceptron again. If the perceptron generates any incorrect results, the learning rule in step 2 will be applied again. And in step 4, you will keep running this process over and over and over until it converges, until the perceptron correctly classifies all members of the training set. Okay? This procedure that I'm going over here, we're introducing it in old-fashioned perceptrons. It is still the same procedure that's used in deep learning. The most modern deep learning networks essentially use the same 4-step procedure here. Start out with random values because you don't know what they are supposed to be. Run through your training set. No errors. Use the learning rule to come up with an adjustment based on all those errors. After you've adjusted the weights using the errors that you found, run it again. Run all the training data again. And keep doing this over and over and over every time, seeing what it got wrong and using what it got wrong to nudge it just a little more towards the right answers. And keep doing this over and over and over. Eventually, for a perceptron, if the problem is learnable, the perceptron weights will converge to a proper weight set, and the perceptron will have learned what you were trying to teach it. Now, I said that with deep learning, we use exactly the same procedure. That's true, only with deep learning, we don't have the guarantee of step 4. In deep learning, in multi-level networks, something may be learnable, but you may not learn it. Oops. So what do? Well, you often will run the whole learning rule, the whole learning pattern, right? This whole 4-step process that itself iterates, but you'll run it multiple times, starting with different random initial weight values, and take the best one you find. So maybe I train it with random weights, and I get a 96% accuracy on my testing data. And then I start again completely from scratch. And this can take sometimes days to run these things. I start completely from scratch again with a new set of random weights, and I run it again, and I get a 94% accuracy, and I go home and make myself a strong drink because I just wasted a day and got a worse result. But tomorrow, I run it again with random values, and maybe I get a 98% accuracy, and I go, woohoo, and go out and celebrate. See, any excuse to go, never mind. But that's what you have to do on deep neural networks, as we'll see. But on perceptrons, if the problem is learnable, and I keep saying if the problem is learnable, and you'll understand why I'm saying that if, but if the problem is learnable, the perceptron learning rule is guaranteed to eventually get you to that solution, is eventually guaranteed to teach the perceptron to solve that problem. As long as the poor little perceptron is capable of learning how to distinguish these two categories, the perceptron learning rule guarantees that it will teach the perceptron properly to do that. Of course, you don't generally know in advance whether the problem is learnable or not. So the devil is in that if. So let's try to start making this concrete, okay? Because I'm the kind of guy, I need to see a real example, or I just get lost in the words. So here is an example, okay? Here's a training set that has 6 items in it, okay? And you can see the items, they're these little circles, okay? And they're plotted here on a little graph. And this graph has 2 axes. It has the x1 axis, which we would normally call the x-axis, and it has the x2 axis, which we would normally call the y-axis, right? And these guys, these inputs are plotted here. So this is an input space that represents a 2-input, or a problem that we would use a 2-input perceptron for. So, in other words, this one only has x1 and x2. There aren't any other inputs. So you got 1 input and 1 weight, 1 other input and 1 other weight, and you also have a 3rd input that's always set to 1, and its weight is minus the threshold. But this is a pseudo input, right? But the real inputs, there are 2 inputs, x1 and x2, with a weight 1 and a weight 2 associated with it. So because if we were to look, we would see that, well, if you think about it, the way I have this shown, it goes from, right, you got 1, 2, 3, 4. So essentially, if you think about the places, the slots in this thing, you can put something at 1, 1. So x1 is 1, x2 is 1, or 2, 1, x1 is 2, x2 is 1, so that's 2, 1, 3, 1, there could be something at 4, 1, there could be something at 1, 2, there could be something at 2, 2, there could be something at 3, 2, at 4, 2, etc. There are 16 positions in this little world. So this is a very, very, very simplified problem, right? So there are only 16 possible positions in this little world. And we're starting out with some training data that has 2 classes, the don't fire class, which is class 0, and the yes please fire class, which is class 1, okay? And I've plotted these things. Class 0 is 1, 1, 1, 2, 2, 1, and 2, 4, okay? And I put them in gray because it's not supposed to fire on class 0, okay? And here is class 2. There's a 3, 1 and a 3, 2, okay? So this is our training data, and we want the perceptron, when it's presented with any of these guys that are shown in gray, we want it to not fire. And if it's presented with these inputs that are shown in yellow, we want it to fire. So this is the training set shown visually. It's exactly the same information that I'm showing by just showing the input points and what class they belong to, okay? And we want to teach this perceptron to learn this. And then we're going to give it new inputs and ask it to tell us what class those inputs probably belong to. So our goal is to teach the perceptron to fire on the 2 inputs located at position 3, 1, and 3, 2, and to avoid firing on other training inputs. And again, note that when I say the position at 3, 1, I mean the order pair x1 equals 3, x2 equals 1. So you can think of our inputs, if you want to, as vectors, right? You can think of our input 3, 1 as a vector over 3 up 1. Now, since we're going to use the implementation where we have a fixed threshold at 0, there will always be a 1 at the front, okay? There'll always be a 1 at the front here because you always set X0 to 1. Okay? Does that make sense? Are there any questions at this point that I need to answer before I move forward? Okay, I think we're still going good here. So let's look at what the perceptron would do initially. Well, initially I would need to give it some weights, okay? And so what I'm showing up here is what the perceptron would tell me if I give randomly assigned weights of W0 being a -3, so in other words, a threshold of 3, W1 being 0, in other words, ignore it, and W2 being 1. So the weight 1 means ignore input X1, right? And W2 being 1 means, well, you'll just use whatever was the input for X2. So these are the randomly assigned weights. I could have chosen any weights in the world, so don't get hung up on where did these numbers come from. They came from, you know, the ether. They're just randomly selected. They could be anything to start with, okay? So given these weights, what happens is that you end up with the perceptron firing on this input. Now remember, it was not supposed to fire on that input, but it's got random weights, so it hasn't learned anything yet. We haven't taught it anything yet. So it just so happened that it says, oh, I'm firing on this guy. Now we were pretty lucky because these three things here, I've got little green circles around them. They happened by chance to be categorized correctly because they are not firing, they're gray, they're not firing, and they're not supposed to fire. So these three inputs, 1, 1, 2, 1, and 1, 2, just so happen that they are correctly classified, so they have a little green arrow, little green circles around them, meaning, oh, these guys are correct right now. This guy has a red circle because it's mischaracterized, and it's yellow because it misfired, okay? These guys over here are gray, which means they didn't fire, and they've got red circles around them because they're incorrectly classified. You were supposed to fire on these guys, and you didn't. By the colors here, you can see that there are two kinds of errors that you can make. You can make false positives, and you can make false negatives. This isn't just true of perceptrons, this is true of any type of classification system. In a classification system, you can have false positives or you can have false negatives. A false positive occurs when the perceptron fires. It fired on this guy when it should not have. So this guy at 2, 4 is a false positive. The neural network, the perceptron, is positive that it's a member of that it should fire on this guy, that it's a member of fire on this set. But it's a false positive because in reality, it should not have fired on that guy. These two, which are in gray, are false negatives. The output is not fire. It's negative. It's not fire. But it's false negative because it should have fired on these guys. They should have lit up. They didn't light up. They stayed gray. And because they stayed gray, when they should have lit up, that is a false negative. Now, false positives and false negatives, like I said, exist in any kind of classification system, and they're very important. If you think about coronavirus is in the news right now. Well, if you take, I don't know if how many of you have taken the coronavirus test, right? They're available free. This may be the last week, but over at the Argent Pavilion, near the football field, But a test to see if you have COVID-19 can give you false positives or false negatives. A false positive means the test says, yes, you have COVID-19, when you actually don't have COVID-19. That can happen. You can get a false positive. You can also get a false negative where the test says, oh, you don't have COVID-19, but you do have COVID-19. So that's a false negative. And so whenever you're building some sort of a classification system, some kind of a medical test, some kind of a system, you have to always be aware of your false positives and your false negatives. And generally, you want to minimize these false positives and false negatives as much as possible. Now, sometimes in the real world, it's better to lean in one direction. Like if you think about COVID-19 and a test for that, false positives are probably less damaging than false negatives. If you get a false positive, the test says you've got COVID, but you don't. So what do? Well, you isolate for 2 weeks. Well, that's a pain, and you don't want people to isolate when they don't have to, right? But that's probably less dangerous than a false negative, because the false negative says, oh, nothing to worry about, you don't have COVID, and you go to class and, you spread it to 50 people. So we have these two different kinds of classifications, but that doesn't mean that they're always equal in how bad they are. In some systems, a false positive can be worse than a false negative and vice versa. But we're going to focus on minimizing both of these because we want our perceptron to give us accurate results. Let me pop out over here because I see there are some comments. I see one question, this was probably from a while before. If we're going to negate the input, why do we even have the input? You probably mean there, Eric, if we're going to ignore the input, why do we even have the input? I'm showing you, I actually picked that on purpose, a weight of 0, to show you that the learning rule, when you randomly assign weights, those weights may ignore an input at first, but the learning rule is going to adjust those weights. And I picked that on purpose to show you that no harm will be done, even if you set all of your weights to 0. The learning algorithm will correct that problem. It might take it longer, but it will. So the learning rule, maybe you start off ignoring an input, but the learning rule is going to change those weights. So we're not screwing anything else up by setting a 0 weight. That was a very good question. So yes, in the first round we are ignoring X sub 1, but we won't always ignore it. The learning rule is going to change the weights. And I see someone talking about someone had a false negative, and that can be problematic. Yeah. No. So it can happen. And it has, thank you for sharing that, it has real world consequences, these false positives and false negatives. But anyway, let's return now to our lecture. Okay. So you might see that there's a gray line here. Okay. And I've got a little plus on this side of the line and a little minus on this side of the line. This line represents what's called a decision surface. A decision surface. And everything on the negative side of the decision surface is going to be, the perceptron will not fire. And everything on the positive side of the decision surface, the perceptron will fire. What will happen over time, I'm jumping to the end here, is this is what we want, okay? This is by random chance where we started. The learning rule that we're about to go over will move the decision surface around And after many iterations, this is after pass 6 in this case, the decision surface will be such that everything is properly characterized. Everything on the plus side of the decision surface is fires, and everything on the negative side of the decision surface does not fire. We're going to go through the math and the details, but essentially what's happening is that this decision surface moves around. The learning algorithm is just changing the orientation of the decision surface, and it's moving it so that eventually the decision surface separates one class, the class that you fire on, from the class that you don't fire on. The only thing the perceptron learning algorithm does is move the decision surface. And for a perceptron that only has 2 inputs, right, the decision surface will be a line. This is why you will sometimes hear people say that the only thing a perceptron can learn is a problem that is linearly separable. There's a lot of shades of meaning in there that we're going to have to dig into, but if you take it as given that the decision surface in a 2-input perceptron is just a line, okay, and all the perceptron learning algorithm does is adjust the orientation of that line, then as long as the problem is linearly separable, you'll be able to solve it. But let's say that I had wanted 1, 4 to be part of the positive group, so that the positive group was 1, 4, 3, 2, and 3, 1, and the negative group is, well, what I'm showing here. That problem, no matter how long you ran the perceptron learning algorithm, it would never converge to a solution, because if you were supposed to include an input here in the positive set, there's no way that you can draw a line that could separate all of the yellow dots, assuming there was a yellow dot right here. There would be no way. So where my cursor is, there's a yellow dot. There would be no way of drawing a single line, a single straight line, that would separate the yellow items from the gray items. So that problem is not linearly separable and would not be learnable by a 2-input perceptron. Okay? And again, we're going to talk about the details of all that more, but I wanted to let you know what this little gray line here was. Okay? Now, the gray line is simply shown at x2 equals 3. x2 equals 3. So when x2 is equal to 3, that's our decision surface. Well, you might be jumping ahead, but if you think about this, because W1 is 0, X1 is ignored at first, right now. So the only input we have is X2, which is multiplied by W1, and we're subtracting a -3. So this line, this decision surface, is the line where you get a 0 as your output from your little equation of your weighted sum. The weighted sum is always going to be 0 along this decision surface line. So if it's greater than 0, it fires. If it's less than 0, it doesn't fire. Is that beginning to make a little bit of sense there? Yes, hopefully. Okay. So let's look at the math behind these decisions. Well, this is the general equation that we gave. It's just the dot product of x times w, but I've broken it out component-wise, right? So 1 times first input, which is x0, which is always 1, 1 times weight 0, which is minus the threshold, plus x1 times weight 1, plus x2 times weight 2, plus x3 times weight 3, plus dot, dot, dot. xn times wn. That is the weighted sum of the input. If it's greater than or equal to 0, fire. Otherwise, don't fire. Well, we don't have n inputs. We only have 2 inputs, x1 and x2. You might say, Mike, we have 3 inputs because we have a 1 standing here. Yes, that's true. We do have a 1 at the front of it. But the real inputs are x1 and x1 and x2. So this is the equation here that our little 2-input perceptron is using to determine whether or not it should fire, right? If the weighted sum of its inputs are greater than or equal to 0, fire. So now let's look at, I said we were going to use a weight 0 of -3, so a threshold of 3, that weight 1 was going to be 0, and weight 2 was going to be 1. So the perceptron will fire when x2 is greater than or equal to 3. Why is that true? Well, because 1 times -3 is -3, plus anything times 0 doesn't matter. So these things give you -3 plus x2 times 1. So it's basically -3, plus x2. Is that greater than or equal to 0? Well, when is it going to be equal to 0? When x2 is 3. Because you'll have 1 times -3, nothing, and 3 times 1. So -3 plus 3 equals 0. And again, that is why this decision surface line is sitting at x2 equals 3. Does that make sense? So now mathematically you know why this line is here. It just falls right out of the equation with the random weights that we've given it. Okay? Now, we said that 2, 4 is a false positive because it shouldn't have fired, and it did fire, false positive. And we've said that 3, 1, and 3, 2 are false negatives because it didn't fire on them, but it should have fired on them. Okay? So let's look at the math for it. Okay? 3 1s is a false negative as it does not cause the perceptron to fire. Why doesn't it fire? Well, 1 times -3 is -3. This doesn't do anything for you. Plus 1, -3 plus 1, -3 plus 1 is -2. -2 is not greater than or equal to 0, so we do not fire. 3, 1 does not fire, but it should have, so it's a false negative. 3, 2, likewise. 3, 2 is a false negative, right? 1 times -3 is -3, of course. This is 0, and it was what? It was 3, 2. So 2 times 1 is 2. So you've got -3 plus 2 is -1. That is not greater than or equal to 0, so 3, 2 does not fire. 3, 2 does not fire. However, it should have fired. That makes this a false negative. And finally, if you look at 2, 4, 2, 4, 2 over 2 up 4, 2, 4, it's going to fire, but it wasn't supposed to fire. So 2, 4 is going to be a false positive, as it does cause the perceptron to fire. Why? Well, it's 2, 4. 2, 4. -3 plus 4 is 1. 1 is greater than or equal to 0, so it fires. You should now understand why this is a false positive and why these two are false negatives. Are there any questions? This is the math that made that happen. Okay? Okay. So, at this point, we just got started, and given this training data here, we know that there are 3 errors. 1 false positive and 2 false negatives. What do we do about that? Well, and it just so happened that these 3 worked out right. So that was good, right? Well, somehow we need to use this information about what the perceptron got wrong to make it better, to make it move closer to the solution that we want. Now, we're finally getting down to the perceptron learning rule. The perceptron learning rule is going to use the misclassifications, the false positives and the false negatives, to compute a learning gradient. A gradient is a direction, is what you can think of it as, or maybe think of it as a slope if you want to. But it's basically a direction we need to move, okay? That gradient, that direction we need to move in, will be combined with something called a learning rate. You can think about, if you think about the gradient as the direction we need to move, you can think about the learning rate as, okay, how far in that direction do I want to go? Okay. On this next step of the algorithm. You might say, well, I want to go all the way, so make the learning rate really big. Well, the problem with that is you can get into, you start out here and you know, oh, I'm supposed to move this way. And so you move that way, but you move so far that way that you overshot where you need to go. So next time you're supposed to go this way, and you move, and so you get into this ping pong back and forth where you're moving too far. Now the perceptron rule, unlike the rules we have for deep neural networks, the perceptron rule will finally settle down where it needs to be if the problem is learnable. But a learning rate that's too big can cause the perceptron to learn slowly because it keeps bouncing back and forth and overshooting where it goes. A learning rate that's too small, well, you're just creeping slowly in the direction you want to go. So you want a learning rate that, you know, that's not too hot and not too cold. It's just right. It's the Goldilocks learning rate. But you don't know what that number is. So you guess. That's what you do. You guess. You're going to find that the answers to a lot of things in neural networks is, you guess. It's a lot like cooking. You don't know how much salt to use at first, so you use a lot, then you go, oh, that was too much, and so you use a really little bit the next time, and you go, oh, that wasn't nearly enough, and you work your way towards figuring out how much salt you need to put in the soup. But that's the way it is. Okay, so essentially, when the perceptron doesn't fire on an input that it should have fired on, it doesn't fire when it should have, that's a false negative. And we will add that false negative to an input vector times the learning rate, to our gradient. I'm calling it an input vector. I really probably should call it the gradient there. We're going to add that false negative to our gradient vector. And the reason we're doing that is that it will make the perceptron more likely to fire on this input vector the next time. Okay? So the false negatives, right, we will add those to the vector. That'll make the perceptron more likely to fire on that input the next time, and that's what we want, right? It didn't fire, but it should have fired. It was a false negative, so we want to push it in the direction of firing on that input next time. And we're going to do exactly the opposite for false positives. We're going to subtract false positives because it was positive, it fired, but it shouldn't have. So we're trying to subtract, trying to pull back there. So essentially, in situations where it didn't fire and it should have, we're trying to push it in the direction to fire next time. And those cases where it fired but it shouldn't have, we're trying to pull those back so that it's less likely that it's going to fire on those guys the next time. Okay, so how will it work? This is going to sound complicated, but it isn't, I promise. The math is very simple, and we're going to go through it step by step. But the perceptron learning rule is essentially a 5-step process. You compute a vector, which we're going to call sum of the false negatives, as the sum of all of the false negative vectors. And then we're going to compute a vector called the sum of the false positives. That's the sum of all of the false positive vectors. And then we're going to compute a gradient vector by subtracting the false positives from the false negatives. In other words, the gradient is equal to the sum of the false negatives minus the false positives. You're subtracting the false positives from the false negatives. That gradient is going to give you a direction in which to move. You then will multiply that gradient, which is a vector, by a scalar learning rate, 0.22, I think is what I normally tend to use, giving you a delta vector. A delta is, you use delta to mean change. That's how much we want to change. And then you'll compute a new weight vector by adding the delta vector to the current weight vector. And that's all you're going to do. You might say, vectors, vectors, Mike, you're saying vectors. I don't know what vectors are. They scare me. I remember them from math, and I didn't like them. Don't get nervous. It's not hard, I promise. Okay. So the next thing we need to do is we need to look at these steps in more detail. Okay. Let's see. I'm going to check our comments real quick. Essentially, we make an error function. Yes, that's what we're doing. We're using an error function. And you're using the gradient to find which direction reduces the error. Exactly, Jonathan, for each weight. Exactly. And then you're just going to tweak the settings until it works, even if you don't know how. That's exactly what we're going to do. Let's see. It's the gradients that scare me. The gradients they're not going to be scary when you look at the math. It's extremely simple. How did anyone ever figure out you needed to multiply the gradient by some random scalar? Well, you could always use 1 as your random scalar, which means you don't have a random scalar, right? And that's probably what the person who came up with it did at first. And then they figured out, well, you know, if I multiply it times something other than 1, I can sometimes get more, a better effect. I learn faster. So if I had to guess where that came out with, I would guess that when the person was developing it, Rosenblatt, originally he started out with a 1 as the scalar, which means he didn't have 1, right? Let's see. So a higher learning rate makes it converge faster. Not necessarily, because a higher learning rate could have you overshoot, because all you get is the direction you need to move, Eric. You don't know how far to move in that direction. So if you move too far, you're going to be bouncing back and forth as you get directional information. So a learning rate that's too high is going to make you learn slowly because you're bouncing back and forth. On the other hand, a learning rate that's too small means that you're creepy, crawly, slowly moving in the direction. But in reality, you don't know what it needs to be. So, let's see. Jonathan, you're incorrect when you say another risk about a small learning rate is that you can get caught in a metastable position. For deep neural networks, you would be correct. For perceptrons, as I've said multiple times, if a problem is perceptron learnable, the perceptron learning rule will learn to solve the problem. There's no getting stuck in metastable positions, okay, with perceptrons. And that was one of the things that people really liked about perceptrons, because if an answer was possible, you were guaranteed to get it, okay? But that does not apply for deep neural networks. Yep, you're thinking ahead, yeah. With a single perceptron, the solution is simpler, and it will, if it's possible to converge, if the problem is linearly separable, it will converge. So that's an advantage, actually, of the perceptron learning algorithm over deep neural networks. And you might say, oh, well, you know, but we know deep neural networks work. That's true. But now think back to the 1980s and 90s, you know, when people were starting to look at deep neural networks again, and they were coming up with these algorithms for learning, like backpropagation, and everybody sitting on the sidelines, right, the peanut gallery, you know, were throwing crap out and saying, yeah, but that's not guaranteed. That's not guaranteed, right? And it's true. It wasn't guaranteed. But sometimes things work pretty good even when they're not guaranteed. So, okay. Chris, that's an interesting question, but let's The gradient is just a scalar. It's just a single number. Okay? So I'm not sure 100% what you mean by polynomial gradient. The gradient is just a number, like 0.5. Okay? Okay, so let's go and get back to notes. I'm going to switch from my PowerPoint. I need to switch to my notes. Hold on a second. It's going to look really weird when I review this and I hear myself going home. Let's see. Don't close the microphone. Do that either. I'm trying to move my notes, and I'm not having much luck because the stuff is at the top. All right, zoom through all of this, through all of this. Okay. So what is the perceptron learning rule? Well, we've already covered it, right? I said it's these 5 steps, but now let's look a little more closely at how these steps would be implemented. Okay. The first thing we need to do is we need to get the sum. We need to get a vector, which is the sum of the false negative vectors. So essentially what you're going to do is you're going to go through all of your training cases that are false negatives, and you are going to add them together component-wise. Okay? So we had 2 false negatives, right? We had 2 false negatives. We had 3,1 and 3,2. Those were our false negatives. So, and really, remember, again, sorry, I'm going all over the place here. Remember, 3,1 is actually 131, and 3,2 is actually 132 because there's always a 1 stuck in the front because we're using the fixed threshold, right? So what we need to do to get the sum of the false negatives is we need to add up all of the x0 values of the false negatives, and that is add up all of the x0 values of the false negatives, and that's sum of the false negatives position 0. And then add up all of the x1s for the false negatives, and that's sum of the false negatives position 1, and add up all of the x sub 2 values of the false negatives, and that's sum of the false negatives sub 2. So sum of the false negatives, sum Fn, is a vector with 3 components, 0, 1, and 2. And if you were going to do it in a program, there's your program. For I goes from 0 to n, sum Fn sub I is equal to sum, as I goes to 1 to s, of x sub, as j goes from 1 to s, of x sub ij, where x sub j is a vector in the false negatives. Well, that sounds complicated, but it's not. Because if you think about our example, we've got 2 false negatives, right? 131 and 132. So the first one would just be a 1 plus a 1, right? The second one would be, I guess, a 3 plus a 3. Anyway, and the last one would just be the x sub 2's there. So all we're going to be doing is adding up, this is 131 and this is 132. So we'll be adding up the first part of this one and the first part of this one. So 1 plus 1 will give us 2. And then the next part is 3 plus 3. That'll give us 6. And then a 1 plus 2. That'll give us 3. So that would be the vector. That would be the sum of the false negatives in this case. So ever how many of them you've got, just add them up component-wise. And that gives you the sum of the false negatives. Same thing for the sum of the false positives. It's exactly the same thing. Gather together all of your false positives you probably have a R of them. You've got some variable that represents how many you had. If we had S was 2 in this case, false negatives. In this case, for false positives, we only have 1, so R would just be 1, okay? And so what you got to do is you got to go through and you got to add up all of the components of those things, component at a time. Well, we've only got 1, right? So there's not a lot of adding to do. So you would end up with 1, 2, 4. 1, 2, 4. Because you've only got 1 false positive there. So now that you've gotten your sum of your false negatives and the sum of your false positives, the third thing you do is you compute your gradient by subtracting the sum of the false positives from the sum of the false negatives. And you do it again component-wise, component 0, component 1, component 2, and that gives you a gradient, which is a vector. It's got 3 things in it, three values. It's a vector with 3 components. That's our gradient. That's our direction that we need to move. Then you can see why, I'm sorry guys, you can see why I've converted most of my notes to slides. It makes it easier to talk through them. I don't find myself bouncing around them like I'm doing here. But anyway, so compute the sum of the false negatives, compute the sum of the false positives, compute the gradient by subtracting the sum of the false positives from the sum of the false negatives. Here's how you do it. That gives you a gradient vector. Multiply that gradient vector times a learning rate. And we're going to use 0.22. So a little over a fifth, right? 0.22. And I say generally values between 0.05 and 0.25 are used in general, but you can use anything you want. And so, how do you multiply the gradient times the scalar vector? Well, the gradient's a scalar. You have to multiply it times each of the components, and there's a little bitty J there at the end of the gradient because you're taking the learning rate and you're multiplying it times gradient 0, and then you're taking the learning rate and multiplying it times gradient 1, and then by gradient 2. I've got it broken out right here. 0.22 times gradient 0 gives you delta 0. 0.22 times gradient 1 gives you delta 1. 0.22 times gradient 2 gives you delta 2. That's your delta. It is a vector. You then revise the weights by adding the deltas to the old weights. So weight I new is equal to weight I old plus delta sub I. And breaking that out for our two-dimensional example, weight sub 0 new is weight sub 0 old plus delta sub 0. Weight sub 1 new is weight sub 1 old plus delta sub 1. Weight sub 2 new is weight sub 2 old plus delta 2. And that'll be the updates. And now you've updated your weights. After updating your weights, you would find that our decision surface is now here. It's moved. And notice it's no longer horizontal. It's now got more vertical. It's got a slope to it. And because it's got a slope to it, you'll find that it's now using both the X1 and the Y and the X2 inputs. So even though we were ignoring one of the inputs, the X1 input to begin with, we're no longer ignoring the X1 input. It's learned, hey, that X1 input's kind of important. Now, so that is the learning rule. But what I did next is I went ahead, so there could be no confusion, I went ahead and applied that learning rule to our particular problem here. So we had, as I said, 131 and 132. You add it up and you get 263. That is the sum of the false negatives. You only had one false positive, 124. So the sum of the false positives are just 1, 2, 4. You compute the learning gradient. So you take the 2, 6, 3, and you subtract from it a 1, 2, 4, and that gives you a 1, 4 minus 1. That's your gradient. You then multiply the gradient times the learning rate. So each of these components gets multiplied by 0.022. So the 1 becomes 0.22, the 4 becomes 0.88, and the minus 1 becomes a minus 0.22. That is your delta. You then add that delta to every weight. We only have 3 weights in this case. So the new weights are minus 2.78 for 0, 0.88 for 1, and 0.78 for 2. And so if you were to take that, and you would find that we now have a situation like this. You might say, well, where did this guy come from? Well, if you take the equations, you can convert where they reach 0 to a slope-intercept format, and it is exactly this line. And you see, it did better now, right? Because remember, before it had 3 things that were wrong, right? It was misclassifying 3 things: 1 false positives and 2 false negatives. Well, after 1 iteration, it now says, oh, these 3 things that I got right before, I'm still getting them right. These 2 things that were originally false negatives, they're now correctly classified as true positives. Right? There's little greens around them. That means they're true. These are true negatives. These are true positives. It looks like it's really close. There's only one thing that's an outlier. It's saying, hey, this guy at 2, 4, I'm lighting up on it. It's a positive, but really it needs to be a negative. So that's after 1 training pass. After 5 more passes or 4 more passes, when you got to pass 6, this decision surface will have moved so that everything is correctly classified. Okay. Questions for me now? Questions for the Mike Meister? Everybody's quiet. There are no questions for me at all? None? So that made perfect sense. Okay. Like I said, it seems like it's going to be scary when I start talking about vectors, but it's really not hard at all. The math is very, very simple. You should now be able to program this if you wanted to for Perceptron. and you would be where leading edge computer science was in 1962. But it's still, I mean, you know, it's pretty cool. Okay. So let's look at some questions. Let's examine some questions about this. Question: is the learning process guaranteed to halt? We've already talked about this multiple times. Let's talk about it one more time. Yes, this process will halt if, gigantic if the problem is perceptron learnable. No, if the problem is not perceptron learnable. So Rosenblatt proved that it was theoretically possible for perceptron to learn the training set you presented it with by the perceptron learning rule algorithm if the problem is learnable. So if the problem is learnable, then the learning algorithm will converge on an answer. It will, if it's possible, given 2 inputs, if it's possible to separate the 2 categories with a line, no matter where you start out the line originally, and that's what the random values do, the perceptron learning algorithm will converge on a line that separates the two classes. If there's any such line, if there's not a line, it's going to keep flopping back and forth looking for that line that doesn't exist. So if the problem is learnable, the perceptron learning algorithm will halt with a correct answer, or with an acceptable answer. If the problem is not learnable, it's going to work its little heart out forever looking for a line to separate the two classes, even if no line exists. Okay. So what are the characteristics of a perceptron learnable problem? Well, the first thing is I said that you could take this equation and with a little bit of algebra, you can get it into the slope-intercept version of an equation. So, right? So remember, x2 is just our y, right? And x1 is just our x. And so what's slope-intercept? Y equals mx plus b, right? So this here is the slope, right? And this is the intercept where it crosses the x-axis, the x1 axis. So you can get you can convert this with a little bit of algebra into a slope-intercept a version of the decision surface. So for two-dimensional input, an x1 and a y1 or an x and a y, you can get a line. And that is your decision surface. And all you're really doing is changing the slope and where it crosses the x1 axis. That's all you're really changing. So I did go back again and explain a second time, you know, why when we began with our random values, it worked out that it was x2 times 3, and the reason for that is you know, the x just vanished here. Well, the x1 vanished, so we just had y2 or x2, which is y equal to 3. Okay. What happens when x2 is 0 or w2 is 0? What happens when the second weight is 0? That can happen if you do that and you try to apply the math. You find that the slope would be infinite because the line is vertical and the x2 axis will never be crossed. So if w2 is 0, if you do the math, you'll see that. I'm sorry. You'll see that the line would simply be vertical in that case. Okay. So always any input above the decision surface, the positive side will cause the perceptron to fire. Any input below the negative side will cause it not to fire. And all we're doing is changing the orientation of the decision surface. The orientation of that decision surface completely describes the total knowledge possessed by the perceptron. One way of saying all the perceptron knows is its weight vector, right? That's one way of saying it. Another way of looking at it is, well, all it knows is the orientation of that decision surface, because all training does is change the orientation of that decision surface. Okay. Now, let's step back a moment. And now I'm going to scroll back to my little image here if I can find it. It just won't. It just doesn't love me. Okay. We can see that the decision surface is a line and the orientation of that line is changing. People often refer to the problems that a perceptron can solve as linearly separable. And you can see why people say that, because we have a line here, and the line must be able to separate the class that you're firing on from the class that you're not firing on. Linearly, align, linearly, separate, separable. But people say that and they miss the implications sometimes. The problems don't always have to be linearly separable. It depends on the number of dimensions that you're working in. This is a neuron that has two inputs. It has X1 and X2, okay? Let's imagine a perceptron that only has one input. All right, it only has an X1. It doesn't have an X2. If we plotted out possible values where you only have one input, what would it look like? Well, I only have one input, so my inputs can only be numbers: 0.5, 27.3, -2, 15. They're just numbers in that case. In this case, since we had two inputs, they were ordered pairs: 3, 2, right? Over 3, up 2, right? That's how we plot these things. So if you've only got one input, you can think about all your possible inputs being on a number line. Okay? So then what would the decision surface be in that case? Well, the decision surface in that case would be a point. So maybe it's 32.1. And in that case, anything bigger than or equal to 32.1 you would fire on, and anything less than 32.1 you would not fire on. So for one input, you have a one-dimensional space, and your decision surface is a point. For two inputs, as we can see right here, for two inputs, you can plot your entire space on a two-dimensional grid, and in that case, your decision surface is a line, and we're just changing the orientation of that line. In a one-dimensional world, where all of your inputs fit on a number line, we're just moving where that cutoff point is. So in a one-dimensional world, your decision surface is a point. In a two-dimensional world where you can plot things, your decision surface is a line. In a three-dimensional world, what do you imagine will be the shape of your decision surface? I'm waiting. I'm looking in chat. A plane.
Plane?
Exactly. A plane. So if I have a three-dimensional space, I have an infinite plane, and I can change the orientation of this plane in space. Okay? Think about a volume. I've got an infinite plane that separates the two sides. And all I'm doing now is adjusting in three-dimensional space the orientation of this plane. For one, two, and three-dimensional problems, our brain is built in such a way that it is very easy for us to look at a problem and tell you whether or not it will be linearly separable, whether or not it will be perceptron solvable. Okay? But what happens when our inputs get not 1, not 2, not 3, but 4? Sadly, just like my pet cat's brain was never equipped to learn English or calculus, my brain is not built to be able to tell you or to look at a problem with 4 dimensions in it and tell you whether or not it is perceptron learnable. I can tell you that what your decision surface would be in that case is a cube in a 4-dimensional hyperspace. I can't point to you for physical dimensions, but I can tell you that the decision surface would be a cube within that four-dimensional hyperspace. In general, for an n-dimensional problem, the decision surface is an n-1 dimensional hyperplane. That is the way we describe that. So in an n-dimensional space, the decision surface is an n-1 dimensional hyperplane. So in a three-dimensional space, it's a two-dimensional hyperplane, which is just a plane. In a two-dimensional space, it's a one-dimensional hyperplane, which is just a point, okay? In a four-dimensional space, it is a three-dimensional hyperplane, which we call a cube, okay? So while for simple 1 and 2 and 3-dimensional problems with 1, 2, and 3 inputs, we can quickly see that whether a problem is going to be linearly separable or not. It does not take a genius to know that if our problem, you know, had an extra yellow fire on me dot here at 1,4, that there ain't no line that's going to separate those things. So this problem is unlearnable. But for, you know, higher than 3 dimensions, you can't visualize. Your brain isn't built to, just like my cat's brain's not built for calculus, your brain's not built to be able to see that. But we can still talk about it. We still know mathematically that in n-dimensional space, it's an n-1 dimensional hyperplane. Now you might start to get to be worried about, well, where are these dimensions suddenly coming from, Mike? All I'm talking about is how many input lines, how many input values do you have going into your perceptron? You know, I drew a little model of a perceptron, and it's like, do you have only one input? Do you have only 2 inputs? Do you have 3 inputs? Do you have 57 million inputs? What are these friggin' inputs you're talking about in the real world, Mike? Okay, think back to that video of that black and white video of the perceptron that recognized men and women. That photo would be digitized into pixels that had some value, let's say 1 to 64, or something grayscale levels, okay? And if you had a 32 by 32 image, you would have whatever 32 times 32 is, that number, that would be how many inputs you would have here, and that would be the dimensionality of the problem. So whatever 32 times 32 is, that number, 1 minus that dimensional hyperplane would have to separate the categorization within that 32 times 32 dimensional space. That's why you can't just look at a problem, a real complex problem, and say whether or not it's going to be perceptron learnable or linearly separable. This is not just a line. It's an n-1 dimensional hyperplane in an n-dimensional space. Okay, so I've given you a lot to think about. You might want to go and look over the notes, because these again are much more in depth. There's a lot more math there. It's a lot more precise than what we were talking about before. We're going to pick it up here next time. I had fun today. I hope you had fun today. We'll see you on Tuesday. Don't forget, your papers are due when? Papers are due when?
Tomorrow at 12.
Tomorrow, no later than noon. So before noon tomorrow, okay?
Excuse me,
So
sir.
be
I
sure
have
to
a
get
question
that.
about the paper.
Okay. Why don't you hold it until after I officially end the lecture? Stay
Okay.
on the line and we'll talk about it. Okay. All right. So I'll see you guys on Tuesdays. Papers are due tomorrow, Friday, the 2nd, before noon. And with that, I'll kill the recording and see you guys then. Bye-bye.